Right, so this is basically a follow-up to my last celestial theodolite video, which basically showed that the celestial theodolite method only gives results that seem to match flat Earth when you have a specific combination of distance to the mountain and delta height between you and the mountain. If that combination happened to fall into the sweet spot, then they would get good results that they thought was evidence for flat Earth. If they didn't have the right combination, then they would get shit results. And it was those shit results, my dear viewer, is what led to the introduction of what Dr. Mike calls the J value. And that's what we're going to look at in this video. So if you've been following the whole saga, you may have seen a graph that looks like this. So you've got three series of data, and the y-axis is the deviation from the predicted value. So for example, Pikes Peak is 4,300 meters above sea level, and these guys claim that using their celestial theodolite star occlusion timing, they can derive a height for Pikes Peak. And as Shane says on the right, the deviations using the flat Earth model are consistently close to zero, typically within plus or minus 1 meter. So in the graph, you got the two globe predictions, one with refraction and one without. Those are the red and yellow lines, which are all over the place because this is a straw man globe prediction. And then you've got this nice blue line for flat Earth, hugging the x-axis perfectly. Now, I don't know about you, but if I'm doing some sciencey stuff and my results are consistently basically perfect, then that should set off some alarms in your head. These deviations of plus or minus a meter are allegedly based on observations that happen over distances of 50 to 100 kilometers. And being accurate down to the meter is just absurd. So just as an example, let's say there are trees 10 meters tall on Pikes Peak, and the star happens to be occluded by one of those trees. Shouldn't you then get a deviation of 10 meters? What if the star was occluded a few meters to the left or the right of the highest point of the mountain? Wouldn't that be at a lower elevation? You can draw your own inferences about what this means for the Ether Cos boys and for Dr. Heffron, but it's never a good inference. All right, so why are they getting near perfect results? All right, this fucking abomination of a spreadsheet is where the data for that graph comes from, specifically the column over on the right, which compares the official height of the peak with the predicted height of the peak using their celestial theodolite bullshit. And as you can see, nearly all of the values are within about a meter of the prediction. And like I said, that should be setting off alarm bells for all sorts of reasons. Now, this spreadsheet literally hurts my soul. And to be honest, I can't believe that it comes from someone that allegedly has a PhD in computer science. It's fucking atrocious. And I'm really not surprised that it took Jesse and Heffron like an hour just to add a new row, like a new observation to it. And the other thing to notice is the J value in this column here. That's what we're going to look at shortly. So what I did is make it all nice and shiny. So I added two new sheets down the bottom left called Peaks and Observers, just so we're not doubling up on so much data. I named all the columns. So instead of having formulas like this, like I've got to go and look up all these cells, like what is K7, what is J1? The formula in these cells in my spreadsheet now looks like this. And now it reads much more like English, and I actually figure out what he's trying to do. Or this absurdly long formula just to convert a decimal angle into degrees, minutes, and seconds. What you could do is use the name manager in Excel to write a lambda function that does it much more cleanly. And then the formula you put into the cell is just, degrees, minutes of this altitude parameter. Yeah, so that calmed me down nicely. Anyway, both of these spreadsheets will be in my GitHub account, and I'll leave a link to that in the description. If you feel like it, you can, double check that I've, exactly replicated the math in Heffron's spreadsheet. And or you could have a look and learn a little bit about how to use Excel properly. All right, now I get to the juicy stuff. I've been pestering Alan for a few weeks now to explain the entire celestial theodolite process, preferably in a one-page document, and explain the J value in particular. So if you remember back to my video a few weeks ago, you go outside, set up a time-lapse camera looking at a mountain, and record the time that a star gets occluded. That is the only measurement you make. All right, so then, as Alan says here, you go into Stellarium, move the Stellarium observer to where the observer actually was, pull up the star from the date and time of the occlusion, and here is the key bit. Let the time play out in Stellarium until the star appears at the globe Earth angle with refraction off. And that time, minus the occlusion time, will give you the J value. All right, so just so everyone is clear, the entire celestial theodolite method involves only one measurement in reality and one measurement only, and that was the occlusion time of the star. And now what they're doing is, quote unquote, correcting the occlusion time and declaring that everything now matches flat Earth to within a meter of the calculated height of the mountain. All right, so here's a typical occlusion. And the measured time of occlusion is 6:43:07. They do their little correction in Stellarium, which gives a time of 6:43:26, which is 19 seconds later. So the J value is 19. And because the celestial theodolite matches flat Earth so precisely, then it matches the predicted height of the mountain by 0.7 meters. Now, my main man, Jesse Path of Light, proposed a hypothetical to the Ethicos crew. I think Heffron was there as well. Doesn't really matter. Anyway, Jesse's hypothetical was, what if there was a huge cloud bank just above the mountain peak? So we don't know it's there. It's dark. We can't see it. But instead of the star being occluded at 6:43 and 7 seconds, it was occluded an entire minute early at 6:42 and 7 seconds. Right, so now the Stellarium time is a constant. It's not going to change. So since the occlusion time was 60 seconds earlier, then you've got to add 60 seconds onto this magical J value, which makes it 79 seconds. And the question was for the Ethicos boys and Heffron, given that the occlusion time happened an entire minute earlier, what error does the celestial theodolite give? Anyway, let's have a play with the spreadsheet and see what happens. All right, so here is Heffron's ridiculously bad spreadsheet, and we're just going to look at the first row. We're just going to use one occlusion timing on the 27th of January at 6:43:07. And you'll see that their result is off by only 0.7 of a meter. All right, so let's apply Jesse's hypothetical. We are going to reduce the occlusion time by 60 seconds. So we'll make that 25:27. Oh, we get an error of 161 meters, but we have to add 60 seconds to this one. So let's go and make that 79 and see what happens. Wow, we're back to an error of 0.7 meters. So, like I said, the celestial theodolite measures only one thing, the occlusion time of the star. But with this J value correction, the actual occlusion time doesn't fucking matter. It's completely irrelevant. So, well played, you fucking Muppets. GG, welcome to the globe, etc.